Uh, oh, I'm getting a pop-up. Okay, good. Good. So what I want to do today is finally move our discussion of two-dimensional CFTs and their relationship to three-dimensional gravity sort of into the modern era. You know, if you look at the outline that I gave at the very beginning of these lectures, we started with Stone Age technology, we moved to Bronze Age, then to the Iron Age. You know, in the classification of the ages of history, it's a little ambiguous what comes after the Iron Age. It might be the Dark Ages, or it could be the modern era. I'm not sure. So I think it's left to the judgment of history whether the perspective that we'll be taking today ends up being the most fruitful one. Okay. But in any case, what we saw is that there are deep and really quite explicit connections between two-dimensional conformal field theory and three-dimensional gravity. So for example, we learned about the remarkable result of Brown and Hanot that you know, predated by more than a decade, I believe, Maldasena's original paper on AdS3, which essentially is the statement that three-dimensional gravity possesses a Virasoro algebra's worth of symmetries, okay? Which is already a powerful connection between gravity and conformal field theory. Then, even more remarkably, perhaps, we learned that this provides a clear and really extraordinarily simple description of black hole entropy as the entropy of some statistical system. That is to say, as the log of a density of states. In particular, we learned that Cardy's formula, which is the formula for the asymptotic density of states at high energy in a two-dimensional conformal field theory, coincides exactly with the expected Bekenstein-Hawking formula for the entropy of a black hole in anti-de Sitter space. Okay. So this, I actually, in some ways, I think of as a more exciting version of, you know, resolution of the black hole entropy puzzle than the one that appears in string theory, precisely because it's such a universal and simple derivation. It doesn't require any sort of fancy D-branes. It doesn't require any, you know, highly supersymmetric, you know, black holes for which one computes an index rather than a density of states. So in some sense, I find this a much more exciting derivation, microscopic derivation of black hole entropy. But nevertheless, we discovered that when you really dig into the details, there are still some puzzles that remain in our understanding of the relationship between 3D gravity and 2D CFT. And one of the most important puzzles is one that I think we encountered yesterday, which is that when we compute exactly, or to the best of our ability exactly, the partition function, or the spectrum of pure gravity, that is to say, the quantization of general relativity in AdS3, we seem to get a continuous density of states. So we discussed at the end of the lecture yesterday one possible way around that by including other sorts of saddle points to the path integral in a somewhat ad hoc manner. There's a different way. There are other cases where you can get a discrete spectrum of states that I didn't have time to go into that are somewhat closely related. But generically, I would say that the most honest version of this calculation in general relativity gives a continuous density of states, which we would summarize by some picture. So here I'm drawing the states, the density of states as a function of energy and angular momentum. And you get some discrete states, such as the vacuum state, or the descendants of the vacuum in the language of conformal field theory, which we call boundary gravitons in the language of gravitational physics. But the important point is that you get these continuous densities of states, which basically follow from the existence of black holes. So in particular, as far as we can tell, there does not seem to be a mechanism directly in the gravitational theory that quantizes the spectrum of these black holes. Okay. On the other hand, in any unitary conformal field theory, we expect a discrete spectrum of states. And indeed, in really any quantum mechanical theory in a system of finite size, we expect a discrete spectrum. And so if gravity in AdS is indeed a standard quantum mechanical system, we would expect some sort of discrete spectrum. Okay. So this is a puzzle. I'd now like to introduce a second puzzle. Okay. And at first sight, this is going to seem like a completely unrelated puzzle. But it turns out that there's a deep and I think very interesting relationship between this puzzle and the puzzle that we just encountered. And this is something that was first discussed, at least in the present context, by Maldacena and Maus, which is the existence of Euclidean wormholes. So what is a Euclidean wormhole? A Euclidean wormhole is a solution of the theory in Euclidean signature. So that's to say it's some sort of Euclidean geometry, which has the property that its boundary, and here of course I mean a conformal boundary in the sense of Brown and Hanot, so an asymptotically AdS boundary. But here now the boundary is not going to be a single surface, but rather the union of two disconnected surfaces. So in particular, these are geometries which have multiple disconnected boundaries in Euclidean signature. Okay. So one simple example of this, so one nice feature of three-dimensional gravity is that such Euclidean wormhole solutions are very easy to construct. In higher dimensions, these Euclidean wormhole solutions are actually rather tricky to construct. They require adding extra sorts of matter and stuff like that. But it turns out that in three-dimensional gravity, they're more or less universal. And a simple Euclidean wormhole solution, which I think is a great one for getting some intuition, is a metric of the sort that I'm writing down here, where d sigma squared is any negative curvature metric. So in particular, this could be the metric on some surface, some two-dimensional surface with constant negative curvature. Okay. And then it's a straightforward exercise for you to check that this is a solution of Einstein's equations with the negative cosmological constant in Euclidean signature. And in fact, if d sigma squared is the constant negative curvature metric on the hyperbolic plane, okay, or sometimes we call that the Poincare disk. So if this is the constant negative curvature metric on the hyperboloid, this is just Euclidean AdS3, otherwise known as three-dimensional hyperbolic space, written in what I like to think of as FRW coordinates. Why do I call these FRW coordinates? I call them FRW coordinates because if I rewrote this metric by doing the change of coordinates t to it, then t will become a genuine Lorentzian time coordinate. That cosh will become a cosine. And then this looks like the metric on a cosmology that has a big bang singularity at t equals minus pi over 2 and a big crunch singularity at t equals plus pi over 2. So this is the coordinate system where anti-de Sitter space looks like an FRW universe. Now, the case where our constant slice is a hyperboloid is not particularly interesting because that's just AdS. Much more interesting, however, is if the metric d sigma squared is the constant negative curvature metric on a compact surface. In that case, what does our Euclidean wormhole look like? Well, it's going to be some geometry with two disconnected boundaries, where the Euclidean time coordinate goes to plus or minus infinity. Now, why is this something interesting for us to consider? Well, what this tells us is that if you were to compute the path integral of a gravitational theory, and you were to do it by summing over all geometries with specified boundary conditions, then Euclidean wormholes of this sort would contribute to the gravitational path integral when you have a boundary that's disconnected. And so in particular, because this geometry is connected, that means this thing is not going to factorize. So what this means is that the partition function of the theory on two disconnected surfaces, at least naively if these Euclidean wormholes contribute, doesn't factorize. But if you believe the AdS-CFT correspondence, where the gravitational path integral is supposed to be a CFT partition function, this can't happen. In particular, this does not happen in a normal conformal field theory. The partition function of a conformal field theory on the disconnected union of two surfaces factorizes. That's practically an axiom of what we mean by a quantum field theory. I should contrast this to the fact that in Lorentzian signature, it is certainly quite common to find geometries with multiple boundaries where the state or the partition function does not factorize. That is to say, for example, the state of the system is not a simple tensor product factor between the state on the two sides of the CF, on two different disconnected components of the boundary. The classic example of this, of course, is a black hole. So I'm not sure if this is something that was discussed at some point last week, but if not, I think it's an important thing to contrast with the situation where I'm describing now, which is that one can view an eternal black hole in anti-de Sitter space as an entangled state where you entangle the state of two different conformal field theories. So that means the theory really, there is some non-factorization between the two boundaries, reflecting the fact that an eternal black hole solution, if you consider the maximally extended geometry, has multiple boundaries. And so in Lorentzian signature, the existence of a solution that interpolates between disconnected boundaries is a feature, not a bug, right? It's reflecting the fact that this is some entangled state in the conformal field theory language, but it's not any sort of problem conceptually. It's in Euclidean signature that these wormholes really lead to a puzzle, because Euclidean partition functions, at least in any sort of standard understanding of what a conformal field theory is, must factorize. Okay. So yes, please.
A small question. Yeah, just wanted to know if these Euclidean wormholes in general pose this problem, but in the particular counting we were talking about yesterday, they don't contribute because they don't satisfy the boundary conditions we had, right?
Good. So yesterday I was declaring that I was going to do a path integral with one single torus boundary. So that means that by the definition, I don't have to worry about Euclidean wormholes. But I certainly could have done a different calculation. And I could have said, well, what is the partition function if my boundary is the disconnected union of two tori, okay? Or the disconnected union of a bunch of other surfaces. You'll note that I've written the surface here. I've drawn my surface as if it has genus 2. rather than being a torus. That's because it turns out that there's no constant, this doesn't work if your boundary is a torus, at least at the level of finding classical solutions, for reasons that we could discuss if you're interested. But the problem, Euclidean wormholes would not contribute to the calculation I did yesterday. I'm now considering a more general calculation, where I consider the partition function not just on a torus, but on, say, a bunch of surfaces that are disconnected. Okay.
Thank you.
Great. So,
I have a question.
yes, please.
So for the case where d sigma squared is a compact surface, you define some Euclidean manifold. Is there a well-defined analytic continuation to Lorentzian signature of this manifold?
Yes. It is the solution to that will become apparent to you if you think about this analytic continuation a little bit. It's just literally the metric that I wrote up here. Okay. This is now an FRW universe, which locally looks like AdS3, but it's a quotient of it in such a way that you have a time coordinate, and the spatial slices are now going to be compact Riemann surfaces. Okay. So this is a genuine cosmology, right? To the extent that one likes to think about such things in three-dimensional gravity, it's one where there's a big bang and a big crunch singularity, and it's a closed universe, albeit one where the spatial slice has non-trivial topology. Good. Any other questions?
So sorry, I thought maybe it's the same as previous question, but is there a Lorentzian continuation of the other case where d sigma square is the compact surface, not
yes.
the...
Yes, that's what I was trying to address. So for example, this metric that I wrote up here, this surface whose metric is d sigma squared could either be compact, in which case it's a cosmology of the form compact spatial slice times time, or it could be non-compact.
I see, okay.
In which case, for example, if it's just the constant negative curvature metric on the upper half plane, this is secretly just anti-de Sitter space, which is written in a funny coordinate system. It's what I call the FRW coordinates of anti-de Sitter space. Well, and what lots of other people call the FRW coordinates of anti-de Sitter space as well. Okay, usually you think of anti-de Sitter space as a static space, but of course this is a theory of gravity. So static is in the eye of the beholder. You could always choose a different time coordinate and then it doesn't look static.
Mm-hmm.
Good. Any questions? Great. Okay. It turns out that these two apparently quite different puzzles have a solution, share a common solution. And the proposed solution that solves both of these puzzles, if we think of gravity not as being described by a single conformal field theory, but instead as an average over many quantum field theory, many conformal field theories. So what do I mean by that? What I mean precisely is that gravity, as defined by some sort of path integral over, so here we're imagining very schematically an integral over a space of geometries with some prescribed boundary conditions. And the proposal is that this is not a single CFT partition function, but the average of many CFT partition functions. So it would, what do I mean by that? I mean very literally that this would be a sum over some family of CFTs that I'll label by a parameter C of those CFT partition functions weighted by some probability density. So this is literally, if I think of that function P of C as a probability density, the average of the CFT partition functions over some family. Okay. So now why could such a picture solve both of these puzzles? Well, this solves puzzle number 1, since the average of a bunch of theories with discrete spectra can have continuous spectrum. So the motivating example that you're supposed to think of when you think of this is random matrix theory, where if I took some n by n matrix and any particular n by n matrix, let's make it a Hermitian matrix, say, any individual n by n Hermitian matrix has a discrete spectrum of eigenvalues. If you think of that Hermitian matrix as a Hamiltonian, then that means that you're considering a n-dimensional quantum system with a discrete spectrum. Okay, the spectrum of the Hamiltonian is a bunch of numbers. But if you average over an infinite family of such Hamiltonians, then there's no reason that the resulting spectrum of the averaged theory should be discrete. So for example, and I think this is a great exercise, let's just imagine that we had a 2 by 2 Hermitian matrix. Then it's a straightforward exercise and a fun exercise to compute the eigenvalue density of an ensemble of 2 by 2 random Hermitian matrices with Gaussian probability density. So what do I mean by that? I mean that the probability that you have a particular Hermitian matrix is going to go like e to the minus trace of h squared. And just for fun, you could throw in some variance there that I'll call sigma. Okay. So this is a fun exercise. You basically just do a change of variables and you do an integral. Here, it will boil down to an integral over the space of 2 by 2 unitary matrices. Okay, so that's a very easy integral to do. But in fact, there's an entire theory of random matrices where you consider not just 2 by 2 matrices, but n by n matrices. And you consider not just Gaussian probability distributions, but very general probability distributions. And in fact, I don't want to spoil what's going to be discussed next week, but it turns out that there is a theory of gravity, namely Jakob-Teitelbaum gravity, which is a theory of gravity in 2 dimensions, where it can be proven with some degree of rigor that the gravitational path integral, in the sense that I have written above. So here, this is a path integral of a 2-dimensional theory of gravity, defined as an integral over 2 manifolds, now whose boundary is a circle regarded as a Euclidean time circle, with some periodicity beta regarded as an inverse temperature. And it can be proven that in some very sort of precise sense, this is an integral over a space of Hermitian matrices with some probability distribution, highly non-trivial probability distribution, of trace of e to the minus beta h. So that this gravitational partition function, the thing that computes the spectrum of the theory, the thermal partition function of the theory, is not trace of e to the minus beta h of any particular Hamiltonian, but instead is the ensemble average thereof, with some highly non-trivial probability density that in fact you can't even write down in a simple closed form. Okay. I added a sort of squiggly line in that equal sign there because there's some subtleties that I assume you'll hear about next week.
May I ask a question?
Yes, please.
Is there a necessary and or sufficient condition that the spectra have to have in order to obtain a continuous spectra out of the discrete spectrum?
There's an entire rich theory that goes into this. I won't pretend to be the world expert on this theory. For example, certainly the probability distribution needs to have support on an infinite number of different matrices, because the average of a finite number of discrete spectra is always going to be discrete. But there's in general a very rich theory behind this, and of course there are conditions that you would want to impose. Well, okay. Aside from that, I don't have anything terribly interesting to say. Good. For example, the probability distribution that appears in JT gravity is rather strange looking. Okay. I think there's some formal sense in which it's not even positive definite. Okay. That is fortunately not going to appear in the examples that I'm going to try and discuss in more detail today. Okay. Good. Okay. So what about the existence of Euclidean wormholes? Well, this perspective on gravity as some sort of average also solves the puzzle raised by Malony and Maus, simply because if you identify the gravity partition function on some surface as an ensemble average, of a CFT partition function, then the thing that you're averaging will be a 2-point function, which simply might not be, and in general will not be, the product of a bunch of 1-point functions. In particular, whenever you have a random variable with a probability distribution that's not delta function supported, but is some non-trivial probability distribution over multiple elements, then the correlation functions aren't going to factorize. So in this interpretation, the wormhole contribution, so for example, the contribution to the partition function of the Euclidean wormhole described by Malony and Maus, does not describe a non-factorization of an individual conformal field theory, but rather, in the language of probability theory, is the covariance of the distribution. If sigma 1 were equal to sigma 2, this would be the variance. If sigma 1 is not equal to sigma 2, this is the covariance.
Can I ask a question?
Yes.
Do we want the space of CFT to be continuous then and not discrete?
I have not. We will get to this.
But I mean, from what you said that, the probability distribution should not be delta function supported. So
it should not have the probability. Okay. The space of conformal field theories is not well understood in general. Certainly to get a continuous density of states, you need to average over an infinite number of elements of an ensemble. But whether these are arranged into some topologically continuous manifold that you integrate over is not something that we know in general, but it will be the case in the specific example that I understand.
Okay, thanks.
Good.
Can I ask, I know it's still much debated, but what's your understanding of, if this is the way to think about the bulk dual of this average, what's your understanding of the relationship between that and the bulk dual of a particular example drawn from the average?
Let me discuss that. That's actually one of the things that I want to talk about momentarily.
Great.
That I assume is something that will be much discussed next week in the lectures by Saad and Shankar. But let me ask, first of all, just from a sort of, 60,000 foot, 19,000 meter perspective, whether this is plausible. Just from a physically intuitive perspective. Okay. So I really think that there are, this idea then is that the thing that we've been calling gravity is not a quantum theory in the usual sense. but it is an average of many quantum theories. Okay. So before we try and dive into any details, let's sort of see if we can think about examples where similar sorts of things occur. And it turns out that stuff like this happens all the time in condensed matter physics. In particular, there are condensed matter systems which are disordered. And when I say they are disordered, that is to say they are theories with many, many coupling constants that are essentially random. And such systems are typically very hard to study. Unless you average over these couplings. So the typical example of such a system would be a spin glass. Okay. Now, what is a spin glass? A spin glass is an actual chunk of material with a Hilbert space and a Hamiltonian that is a normal quantum system. But the problem is that we don't know how to study that quantum system. So instead, what we do is we do a trick where instead of saying that this is a chunk of material with a bunch of couplings that are essentially random, we consider the ensemble of such chunks of material where you treat the coupling constants as actual random variables. Okay. And the point is that the individual pre-averaged chunk of material is impossible to study, but the post-averaged thing is easy to study. So when one performs this, sorry, let me just finish this sentence.
No problem.
This disorder averaging, you obtained a simpler theory that is easy to study. And perhaps general relativity is an example of such a theory that is easy to study because it has been disorder averaged. So in this analogy, general relativity is a simple theory, that is to say an averaged theory, and the complicated theory, the pre-averaged theory, would be something like maybe string theory, or maybe some other complicated theory. So in the language of AdS3, where the individual theories of gravity would be instances of the ensemble of CFTs, that is to say the complicated, the analog of an individual spin glass with a Hamiltonian and a Hilbert space would be a conformal field theory. And general relativity is the theory that emerges when we try and make our life simple by averaging over these zillions of coupling constants drawn from a distribution. Good. So that's one sort of context in which this disorder averaging might make sense. There was a question?
Can I ask a question? Oh.
Yeah.
Someone else had a question before me.
You answered my question with your last sentence, so that was good. Thank you.
Other question?
Yeah, my question was, so you're saying that this gravitational theory, GR, is an average of another gravitational theory, the string theory?
Well, maybe. That's the picture. Okay. That's the picture that you're supposed to. That's one picture. I'm going to present two other ways of thinking about it just now. Okay.
Excuse me, can I ask another question?
Sure.
Here you mentioned that, okay, GR might be the simple post-average theory and string theory, the general complicated one. It's maybe a naive question, but is it obvious that we don't have only GR, in the sense that GR maybe it's the simple post-average theory and it's an emergent feature when you average over the ensemble, but maybe there is no actual dual to a single state or to a single CFT instead?
I don't have anything useful to say about that question. I mean, certainly the best understood examples of AdS CFT are theories of gravity that have a single CFT dual. N equals 4 Yang-Mills is a theory. It's not an average of many theories. And its apparent dual, checked to astonishing accuracy, is type 2 string theory compactified on AdS5 cross S5 with specified boundary conditions. You know, this has been checked to extraordinary detail, not just classically in the bulk, but to some extent quantum mechanically as well. So, you know, that's a theory. That's an instance of the theory. So certainly we have extraordinary amounts of AdS evidence for AdS CFT as relating instances of theories of gravity to individual conformal field theories. The perspective I'm taking here is that those are very complicated theories of gravity, except in certain limits, like N equals 4 Yang-Mills is in a sense integrable. So it's dual to, at least in the planar limit, it's integrable. And so it's dual to some presumably integral theory of quantum gravity.
The idea is that it's reasonable to expect that for any low energy GR theory, which is an ensemble, we should be able to have a UV completion, which is equal to each CFT of the ensemble.
But many possible completions, right? In the same way that the averaged theory of a spin glass is describing an ensemble of many, many, many possible chunks of material. So that's one perspective.
I have a question.
Okay, yes.
So in what sense do you like have unitarity once you start averaging over theories?
The individual instances of the ensemble are unitarity. That is the sense in which the theory is unitary. Right? That's pretty good. What else could you ask for?
So then GR would actually be considered, like GR as a disorder average would actually be a non-unitary theory.
It's unitary in the sense that okay, if this picture is correct, it's unitary in the precise sense that it's an average of many unitary theories. Averages of unitary theories have properties that are not the same as the individual unitary theories.
Okay.
Sorry, I have a question.
Okay, yes.
Can you interpret this ensemble coming from some vacuum manifold of some UV, say, completion?
Let's discuss that later on. That's actually related, not unrelated to things that I'll be discussing.
Okay.
Okay. There's another point that I want to make, which is that averaging has already appeared. It appeared in the lectures that you saw last week in our discussions of black hole entropy. But the sort of averaging that appears is one where we coarse grain over states, not where we average over theories. Right? But in particular, what do we do when we average over, when we think about black hole entropy? You think about individual black hole microstates. These are quantum states that are not geometric. You know, they're states of some very complicated quantum mechanical system. You know, there's this sort of fuzzball approach where some of these states at least can be regarded as a quantization of the space of geometries. Generically, however, a black hole microstate is not some sort of geometric object. But the black hole geometry is something that emerges only after averaging over such states. This is a different kind of average, however. It is a coarse graining average. That is to say, it is the kind of average that you always do in statistical mechanics. So in particular, it's the average where you fix the theory that you're in, but you average over some number of states in the theory, fixing only macroscopic properties of the states and ignoring microscopic properties of the states. You know, you'd study the gas in this room by fixing the temperature and pressure, but averaging overall, you know, Avogadro's numbers worth of states which are consistent with those macroscopic variables. But the point is that in various condensed matter systems, there is often a relationship between this kind of averaging and ensemble averaging. So in particular, in some types of theories, which are sufficiently chaotic, and the magic words that one often says here are self-averaging theories, the average over states is indistinguishable from an average over coupling constants. That is to say, an average over theories. And when I say indistinguishable, I mean indistinguishable for sufficiently coarse observables. Okay. And in fact, if you ask me what I actually believe, not that you did, what I actually believe is that perhaps ensemble averaging is coarse graining, and in particular is the remnant of coarse graining that remains after dimensional reduction and taking a near horizon limit. So in particular, let's imagine that we have this picture where we have some sort of black hole in higher dimensions. So what is the coarse graining procedure? Well, let's imagine that you have a black hole microstate or a set of black hole microstates in some asymptotically flat theory of gravity in higher dimensions. Maybe it's in 10-dimensional string theory. Okay. Then, of course, if we were to perform some sort of coarse graining where we average over states, say, with a fixed mass within some window or something like that, then you're going to get a black hole geometry in higher dimensions. Now, what is the near horizon limit of a black hole geometry? Well, at least for the extremal black holes that we understand well, if you took a near horizon limit, then you would get some AdS factor. And in particular, if you took a near horizon limit and did some dimensional reduction, you would get some factor, say, of AdS2. AdS2 if it's an extremal black hole, or AdS3 if it's an extremal black string. So then the conjecture is that you can complete this square to make a diagram that commutes. In particular, you could do the analogous dimensional reduction procedure for the individual black hole microstates to obtain an individual family of conformal field theories which, when we ensemble average over them, we would get a theory of gravity in AdS2 or AdS3. So again, this would be some sort of procedure of dimensional reduction.
I'm a little bit confused about this picture. It's a really nice, yeah, it's a really nice picture, and it'd be great if something like this.
Yeah, I think this is very plausibly where ensemble averaging comes from, but I don't have an extraordinary amount of evidence for this. I bring this up only as one possible way that we could think about this ensemble averaging.
Can I just ask how you would see this working in something like n = 4 and D3 branes, for example, because I would think there that the coarse graining in the black hole microstates is still coarse graining in the CFT states, not over a space of CFTs.
It's crucial to take a near horizon limit. And that's going to be crucial. Yeah. But what I do not have is a precise calculation. Okay. Mm-hmm. So I'm going to punt on any questions like that. Okay. I have provided here what I think are 3 perspectives on ensemble averaging. But now what I'd like to do is try and make this precise. So in particular, I would propose the following strategy to make this precise. So to understand gravity, as an ensemble of CFTs, what do we need to do? First, we need to find some family of conformal field theories that we can characterize precisely. Second, we need to find some probability distribution over this family. And third, we need to start computing things where we average over this family of CFTs and compare to our gravitational expectations. Okay. Now, let's first imagine trying to do this for all conformal field theories. So the problem of classifying all conformal field theories has a name. That's the conformal bootstrap problem. It has a name because it's hard. We don't give names to things that are easy. You know, I'm sure Eric in his lectures next week will talk in great detail about the conformal bootstrap problem. Even in 2 dimensions, the conformal bootstrap problem is a very difficult one. And with the exception of certain very special families of conformal field theories, such as the rational theories with low central charge, or theories with an extraordinarily large number of symmetries, we don't know how to classify that family of CFTs in general. So instead, what I'm going to do is what we always do in physics when we have a problem that we can't solve, which is I'm going to add symmetry to the problem until I can solve it. So in particular, how do we add symmetry in a conformal field theory? Well, in a conformal field theory, the symmetries of the theory are generated by chiral operators, right? The statement that an operator is chiral is the statement that it is a conserved current, right? You know, d bar j equals 0 for some chiral operator j is the conservation law for a current whose z bar component is j. So that means that we're going to look at CFTs, which have lots and lots of chiral operators, lots and lots of conserved charges. So what is the biggest symmetry algebra that I could imagine? And the simplest symmetry algebra that I could imagine? Well, the simplest group I can imagine is U1, and the largest group I can imagine that's built out of these is U1 to some power. So in particular, what I want to do is consider this problem for 2-dimensional CFTs with central charge equal to some integer n and U1 to the n times U1 to the n chiral algebra. So in particular, we call these current algebras in the language of CFTs because they're built out of conserved currents.
Sorry, why not the monster CFT that you discussed yesterday?
Monster's too complicated. 196,883, come on. What you think I said, I want to do this something that I can solve. Okay, U1 is much simpler than the monster group.
Okay, thanks.
Okay, it turns out that the family of conformal field theories with this current algebra and central charge is known. It is finite dimensional. And it's something that you can describe completely explicitly. it turns out that there is, in a sense, a unique natural probability distribution on the space of CFTs. And perhaps most remarkably, it turns out that there's a beautiful mathematical theory that allows us to average whatever we want over this space of CFTs.
Can I ask a question?
Sure.
It's not, from what you've said so far, it doesn't seem like it's the case that averaging over any family of CFTs with like any probability distribution is going to give you a theory of gravity, right? So it's just a coincidence in this. I mean,
So
I assume you're going to tell us.
For the family of CFTs, I probably won't have time to get into details. For the so if you have a continuously connected family of conformal field theories, then there is a natural metric on this family. Why is that? Well, two nearby conformal field theories are related by a marginal operator, okay? Because you add a marginal operator to the action of a CFT, that's because it's marginal, it's dimensionless, so you get another CFT, okay? So then the 2-point functions of that marginal operator define a natural metric known as the Zamolodchikov metric on the space of CFTs. And when I say there is a natural metric, that is the metric that I am using. Okay.
It's just going to turn out that this works.
It turns out for discrete distributions, there is a similar natural conjecture that I will talk about if I have time for what the measure should be. Okay. Motivated by number theory, really. Actually, it's pretty natural. But in particular, for this family of conformal field theories, you can average over this family of CFTs of the partition function. So I remind you that each one of these has a discrete spectrum, but I'm going to average over an infinite number of them. Okay. So I'm going to get something that has a continuous spectrum, and it takes the following form. It is a sum over geometries of a classical action plus a one-loop action. That's it. Okay. Remember what we did last time? I tried to compute the torus partition function of pure gravity. I included a bunch of geometries that I could classify. I added a classical term. I found that the theory remarkably was one-loop exact. So I added the one-loop term and I tried the sum. I got something continuous. It turns out that there's a slightly different problem that I could have done, where instead of considering general relativity, I could consider a different theory, which is a sort of exotic theory of gravity.
Is this equation you wrote true for any sigma, including sigma disconnected?
Absolutely, I'm going to get to that. And this is a sort of exotic theory, which is not exactly general relativity, but is something simpler than general relativity that is usually referred to as U1 gravity. So in particular, if you remember what I said earlier when I was talking about general relativity is a Chern-Simons, perturbatively general relativity looks like a Chern-Simons theory for the gauge group SO2, 2. Okay. Here I'm going to replace this with a Chern-Simons theory for the gauge group U1 to some power. Okay. That's going to be my perturbative theory. I'm going to augment it with a sum over geometries. And when you do so, what do you get? You get this average. Okay. And so this is a sort of holographic duality. Where, to the extent that the right-hand side is well defined, we know both sides of this duality explicitly. The price that we pay is that we're considering a simple theory, a very simple theory, one that is much simpler than general relativity. Okay. In particular, I should also mention, which is that this works when sigma is arbitrary. So it's not just a torus, but also an arbitrary surface, or a disconnected union of surfaces. Although in the disconnected case, there are certain subtleties that I don't think I'll have time to discuss. Okay. Good.
Could you give an archive number to the paper that is discussed?
Sure, I'll give a reference. So there's 2 references. So there's the paper I wrote last summer, Witten. And there was another paper on the same idea with a rather different perspective by Afkamijeri, if I'm pronouncing that correctly, Cohn, Hartman, and Tajdini. They took rather different perspectives. So I encourage you, if you're interested, to think about both of them. But let me, I've described this all very abstractly. Okay. Let me just tell you what the theories are that we're considering. The theories that are instances of this ensemble are just free bosons. Okay. It's very simple. Right? The only thing that makes these non-trivial is that they are compact free bosons. Okay. So for example, when C is equal to 1, what is the theory? It's the theory of a single free boson. And in particular, it's going to be a free boson with a compact target space of radius r. Why did it have to be a free boson? Well, I said I wanted a U1 symmetry. Okay. What is a U1 symmetry? It's a rotation symmetry, otherwise known as a translation on a circle. In the language of these free bosons, that's the shift x to x plus constant. Okay. Good. So the U1, and then in a CFT, it gets promoted to an infinite algebra of symmetries in the same way that the Virasoro algebra, if you start with a rigid conformal group, that gets promoted to a full infinite algebra of Virasoro generators. Okay. So in particular, this is the C equals 1 example. It's the simplest possible theory. And the space of such theories is a manifold parameterized by the radius r. So in particular, r is a coordinate on this space of CFTs with central charge 1. Okay. There's a natural metric on this space of CFTs. What is the metric on the space of CFTs? Well, it's going to be a one-dimensional metric with r being a coordinate on that space. So it's going to be something times dr squared, right? It's the only one-dimensional metric I can think of. Okay. And what is that something? That something is easy to determine if you know what T-duality is. Okay. What's T-duality? T-duality is the statement that a free boson at radius r is the same theory as a free boson at radius 1 over r. That means that it has to be a metric that's invariant under r goes to 1 over r. Okay. Exercise. Check that the metric dr over r squared is invariant under r goes to 1 over r. Okay, that's an easy one. It turns out that this is the correct metric on the space of CFTs, and that defines a probability distribution. What is the probability distribution? It's just the volume with respect to that metric. So in particular, when I say an average over space of CFTs, what I mean is literally an integral with respect to that measure. So an integral dr over r, an integral of root g integrated over the space of CFTs. And because I have t-duality and I don't want to double count my theories, I integrate r from 1 to infinity, not 0 to infinity. Okay. Now, the first thing that you might complain about here, and this would be a very good thing to complain about, is that the first thing you would want to try and average is 1. Okay, right? The average of 1 should be 1. That seems like a pretty good place to start. But of course, the integral dr over r from 1 to infinity diverges. Okay? So in fact, what you see is that when you have a single free boson, the volume is divergent. And so you couldn't really use that to define a nice probability distribution. Why do I say that? Because you would want to define a probability distribution by normalize everything so that the average of 1 is equal to 1. That is to say, the integral over the space you're considering is the integral of the probability density over the variable, the random variable, should be equal to 1. This does, you see that the probability distribution I'm trying to define at c equals 1 is not normalizable. Okay. But when c is bigger than 1, it is normalizable. In fact, you almost know this already. Right? Many of you probably know this, although you don't know that you know it. It's a known unknown or an unknown known, one of the two. In particular, let's think about the case where I have 2 free bosons. So for 2 free bosons, what is the target space? The xi, where I run from 1 up to 2, okay, parameterize a torus. Okay. What is the moduli space of this torus? Well, to start, let's remember that we've already spent a ton of time talking about the moduli space of the conformal structures on a torus. Okay. And what is the moduli space? It is the upper half plane mod SL2Z, right? You have that complex parameter tau modded out by SL2Z. So that turns out that's the space of conformal structures of this target space torus. Turns out that there's also a moduli space of Kähler structures, okay? So here I'm talking about the moduli space of conformal structure. That is to say, the part of the geometry that doesn't care about lengths and only cares about angles. The part that cares about lengths, it turns out, is exactly the same. So the moduli space of Kähler structures is exactly the same as the moduli space of conformal structures. That's related to something known as mirror symmetry. Okay? This is the statement of mirror symmetry for the simplest Calabi-Yau manifold in the universe, which is the torus. Okay? So in particular, for 2 free bosons, this is the moduli space. And it is a famous fact that the volume of the fundamental domain of the torus is finite. That's why string theory doesn't have loop divergences, right? String perturbation theory is a loop expansion where you integrate instead over momenta running around in loops, you integrate over moduli spaces of surfaces. And in particular, the one loop integrals in string perturbation theory are integrals over this fundamental domain. This is finite volume. That's why string theory is a theory with no UV divergences. Good. So indeed, it turns out that when you take any number of bosons larger than 1, the volume is finite of the space of CFTs, so we have a good probability distribution. Okay. So we have a space of conformal field theories. We have a probability distribution, so you can compute an average. And it turns out that there is a mathematical theory, much beloved by number theorists and sphere packers, that tells us exactly how to compute such averages. Okay. So in particular, it turns out the average. So let's talk about the torus partition function, just to keep life simple. So what is the average? Well, if you paid attention to the lecture I gave yesterday, the average is going to look very, very familiar to you. It is a sum over SL2Z, and in particular, a particular quotient of SL2Z, of some function of the tau parameter transformed by one of these modular transformations. So here I'm calling C n, I guess. I'll call it n. So this is C equals n. Times some factor that will be very familiar to you from our discussion of loop corrections in AdS3. That is just this, basically a product of a bunch of simple harmonic oscillator partition functions. Okay. So first of all, you'll notice that this, what is this? This was the sum over the SL2Z family of black holes. Okay. That is to say, it included a sum over the geometry that we called Euclidean BTZ, the geometry that we called thermal AdS, as well as the infinite number of other geometries. And what is this thing? This is the thing that we interpret as the classical action plus one loop determinant of our bulk theory, of the bulk perturbative theory. And what's going on here? What's going on is that when we did that calculation in pure gravity, we computed a one loop determinant by counting descendant states. That is to say, boundary gravitons. Here we have exactly the same thing going on, except I've given them a different name. I'm going to call them boundary photons instead of boundary gravitons. In the language that we have been using previously, it's the partition function of states where you take a bunch of descendants of the identity. That is the descendants of the ground state. And you sum over them. That's why you get a bunch of harmonic oscillator partition functions. Okay. Let me just end with a couple of comments, which is that this actually works not just for the torus, but for any Riemann surface. So in particular, instead of taking the torus, I could take a surface that looks like this. This would be some genus 2 surface. In that case, the sum that appears is not the sum over SL2Z, but a sum over some higher genus version of the modular group. I won't talk about that in too much detail, but I'll just talk about the interpretation of the terms in the sum. One interpretation of the terms in the sum is as a sum over handle bodies, where again, I remind you, what is a handle body? A handle body is a geometry where you fill in the boundary cycles in some way. Okay. So in particular, if I were to try and represent this schematically, the average of the partition function on a Riemann surface is a sum over all of the ways of filling in that Riemann surface.
Sorry, just to clarify, the two taus on this page are unrelated. Like the tau that you wrote before is unrelated to the tau. Yeah.
Yes.
Okay. Thanks. Yeah.
So the tau that is appearing here is the modular parameter of the world sheet torus. The tau that appears up here, I should have just, that was the conformal structure of the target space torus. Yeah, great question. Thank you.
Thanks. Yeah.
Good. Okay. So in particular, I'll mention that there is a, so in this sense, you can compute the average of any observable in our conformal field theory. Like if you consider the general partition functions of the theory, the most general observables in a theory, then you can check this, very weird kind of holographic duality for any observable. So we're in a pretty good situation. This is not something we have the luxury of doing for general examples of the AdS CFT correspondence.
Did you say that the partition function for a one genus surface should vanish? Is that easy to see?
So sorry, one genus.
Sorry, genus one.
So no, so the partition function. Sorry, if the world sheet is a sure, C equals 1, you meant, or no?
No, I think I'm confusing myself. I was thinking about earlier when you were talking about the Euclidean wormholes. Never mind.
Okay, yeah, there are no. Okay, one curious thing is that the Euclidean you can also, of course, compute, for example, the torus partition function, but higher moments of it. And of course, it does not factorize because, it's a probability distribution. And not factorizing is what probability distributions do for a living.
So Alex,
Yes.
I want to, I know it's your last lecture, so I want to give you time, but
I'm done.
But I also
like
don't want
minutes.
it to blow out.
Yeah,
but,
I'm 2 minutes from being done.
Great.
Right, up to questions. Thanks. Yeah. So these correlation function, this probability distribution is non-trivial, so things don't factorize. Right? Good. I think the gravitational interpretation of this is still a little bit mysterious. Okay. I mean, it's closely related to discussions of wormholes and stuff that I think Phil and Steve will wax poetic about wormholes if I know them. So you'll hear plenty about that next week. So I think this is a very appealing example of how this kind of averaged holographic duality would work. It's a very simple theory of gravity because we started with a very simple theory of CFTs. And then, of course, you could ask, what about general relativity? And the natural conjecture, and this is just a conjecture, is that the partition function of gravity, as defined by the path integrals of the sort that we've been staring at all week, should be an average not over those CFTs with that fancy U1 times U1 current algebra, but all CFTs. So that's the guess. Not much evidence, not much evidence one way or the other, but if you ask me what I think is true, that's what I think is true. There's even a sort of conjecture that you can make for what the probability density is, which I won't talk about unless people are interested in. I'll just mention that this is, from the conformal field theory point of view, a remarkably strange conjecture, because it means that a typical CFT with large central charge looks like pure gravity, right? That's what ensembles do. That's what this kind of disorder averaging does. A typical element of the ensemble looks like the average element of the ensemble. And in particular, pure gravity has all kinds of features that don't look like most of the CFTs that you learn about. If you pick up, the big yellow book and you flip to a random conformal field theory, right? The measure on the space of conformal field theory is defined by a random page in the big yellow book, okay? Does not give you a typical conformal field theory that looks like pure gravity, okay? So that means that something very strange is happening in the space of conformal field theories at large central charge. So for example, and this is possibly the strangest thing about pure gravity, is that pure gravity has a gap between the vacuum state and the lightest black hole. In the language of conformal field theory, we say that the theory is sparse. So the lightest primary state has dimension of order the central charge. Okay. Now, it turns out, so you could ask yourself, what CFTs do you know of that have a gap in the spectrum of operator dimensions of order the central charge? I personally don't know of any conformal field theories where the gap is larger than 2. Okay. The monster theory that I wrote down the other day is an example of a theory where the gap is 2. 2 is not a particularly large number. Okay. But what this conjecture would imply is not just are there conformal field theories with large gaps, but that a typical conformal field theory has a large gap. This seems like a preposterous statement, but if you believe that pure gravity is an average over a space of CFTs, this is the implication of that. I'll mention that I think there's a lot of intuition to be gained here from thinking about sphere packing, because it turns out that high dimensional sphere packing is a mathematical problem that's very close to the problem of the classification of CFTs. It's sort of like a toy version of the classification of CFTs. And very similar statements turn out to be true for sphere packing in high dimensions. Okay. Turns out that the typical sphere packing, the optimal sphere packing in low dimensions is some beautiful lattice that you can look up in a book. It's the hexagonal lattice in 3 dimensions. It's the Leech lattice in 24 dimensions. But it's believed that the optimal lattice packing in high dimensions is some kind of disordered system. And moreover, it's believed that a typical sphere packing in high dimensions, with a certain measure used to define the word typical, is optimally dense, okay, right? Which is the analog of the statement in the CFT language that the spectrum has a gap that's as large as possible. So I'll just maybe end there. Hopefully I didn't go too far afield in this last lecture with the speculations and the rantings and ravings, but just went exactly far afield enough. Okay, so I'll stop there and see if there are questions. Thank you.
I have a question. So my question is, in the equation above where you define ZGR is this integral and sum, I'm assuming you can't exchange the order and expect the same answer between the sum over CFTs and the path integral.
This expression that I wrote here is supposed to be both a sum and an integral because I don't know what the space of CFTs is. In general, we expect CFTs to be isolated points so that I should talk about a sum here, but there may also be connected pieces of the space of CFTs, in which case you would do an integral. Okay. But I wrote sum and integral at the same time so that you couldn't make me pin me down as to which it was. really it's more properly probably a sum. Okay. Yeah, but yeah, this is an equality. So I'm not integrating, right? So the statement is the integral over a space of 3 manifolds weighted by a Euclidean general relativity action is the sum over all conformal field theories weighted with a particular probability density. And the point of comparison between the two sides is that the Brown-Hanot central charge, that is to say the AdS, radius, and Planck units, is the central charge of the corresponding CFTs on the right-hand side of this equation. And maybe there's a squiggly line instead of an equals in this equation, because maybe you have to average over, so smear over some window of central charge. I think that's probably likely, but I'm not going to talk about that.
I have a couple of quick questions about this last part. The first one is why we expect GR to be an average over all CFTs and not just an average over, again, a particular class of CFTs.
I think the intuition is that the less that you fix about your theory, the larger the space you should average over. Right? I mean, think about statistical mechanics. You fix some macroscopic variables and you average over everything consistent with those macroscopic variables. What is the data that is used to define a theory of gravity? It's, an AdS radius, a Newton constant, and a single dimensionless ratio. That is the Brown-Hanot central charge. What is the symmetry group of that theory of gravity? It's the Virasoro algebra. Hence, average over all things with that algebra. This is a conjecture. This is not supposed to be, may well be totally wrong, right?
Okay.
It's not an interesting conjecture unless it's possibly wrong.
And the other question was the fact that it seems like a typical CFT doesn't have this large gap, or in general doesn't look as we expect gravity to hint.
The typical CFT with respect to the DiFrancesco measure on the space of conformal field theories. Right.
Okay.
The DiFrancesco measure is the measure defined by opening a random page in DiFrancesco and looking at that conformal field theory.
So this that was exactly my question. Like, does it mean that gravity is hinting that we don't know what a typical CFT is, and we don't know an example of a typical CFT, or not many of it?
Yes.
Or does it mean that maybe this interpretation might be not right?
Yes. Okay. So if you believe this interpretation, then that is exactly what I am saying, that we don't know any example of a typical conformal field theory with large central charge. The same is true in sphere packing. We don't know any example of a typical sphere packing in a large number of dimensions. But we can place bounds on the, on the density of these sphere packings and argue that a typical sphere packing for a certain definition of the word typical comes close to saturating that bound. Okay. I mean, mathematicians don't like making conjectures, but if you corner one and don't let them leave without making a conjecture, they'll tell you that's what they believe about sphere packing.
Thank you very much.
I have two questions. So I think the first one, maybe you addressed it, but it seems like the machinery in the specific example you showed involved fixing a particular central charge and then averaging over theories with that central charge and with these like U1 currents. So how would you start if you wanted to average over different central charges as well?
Okay, I mean, I have a favorite answer to that question, which is the following. Okay. This is actually a quite beautiful story. So what is the central charge in the bulk interpretation? Right? So the central charge is the AdS radius. That is stated as the cosmological constant. Okay. What is the contribution to the action of a theory of a cosmological constant? It's the integral root g of lambda, okay? Which by very sophisticated mathematics is lambda times the integral of root g, otherwise known as lambda times the volume of space. Okay? And this is the thing that we insert in the path integral of our theory of gravity. So you insert in your path integral of theory of gravity e to the minus lambda times volume. Okay? So what does that mean? That means that lambda is the, we're doing a Legendre transform where lambda is the variable that is the conjugate to volume, okay? Now, in thermodynamics, you have a name for the thermodynamic variable conjugate to volume. It is the pressure, okay? And so that means that in this analogy, you think of gravity with a particular value of the cosmological constant as a theory of gravity at fixed pressure, right? Cosmological constant is a pressure that weights theories with different, weights space-times with different volume, okay? But you all know thermodynamics, so you know that there's no rule that says you need to work in an ensemble with fixed pressure. You could work in the ensemble with a fixed volume. Okay? That is to say, you work in the ensemble, you fix the thermodynamic variable conjugate to the cosmological constant. There's a beautiful theory of Castor and Trashin, who developed the theory of AdS gravity in the ensemble of fixed volume rather than fixed pressure. In this context, everything you called an entropy becomes an enthalpy. Okay, I didn't know what an enthalpy was until I read this paper. But it's a theory of gravity where you integrate over the cosmological constant to obtain anti-de Sitter spacetimes at fixed volume instead of at fixed cosmological constant. And in the conformal field theory language, this is the statement that you study ensembles of conformal field theories, where you fix a variable that is canonically, that is thermodynamically conjugate to the central charge. Okay. In fact, if you've studied symmetric product orbifolds, if you've studied the DMVV formula, I sort of have a sneaking suspicion it probably showed up in some of Ashok's lectures last week, knowing, although I didn't have the chance to come to them, conformal field theories with potentials conjugate to the central charge show up actually rather frequently. So that might be the sort of thing that one needs to do. Yeah. Good. Was there a second question? Or?
Yeah. Yeah. So my second one is about trying to understand when you might have an ensemble on the gravity side. So the things that you listed that seemed rather pathological were the continuous spectrum and the factorization puzzle. So is there anything else that might hint towards having an ensemble of theories and not just having a single CFT as the dual description?
I mean, there have been attempts to compute, for example, things like this double torus partition function in AdS3 gravity as a from a Euclidean wormhole. So there's a computation of Kotler and Jensen where this is discussed. It's a tricky computation because there's no classical saddle point that contributes. But they have an answer that resembles random matrix theory in some ways. So that I think one could take as a piece of evidence. Okay, I mean, I think, to my mind, the Muldasen and Mao's Euclidean wormhole story is probably the most interesting piece of evidence for this. And the fact that it works very precisely in JT gravity, I think, is the most interesting piece of evidence.
Thanks.
Sure.
Could I ask a question about that, actually?
Sure. I mean, there were other people who raised
their
hands.
hand.
I don't know how we want to. Maybe let's go by the people who have their hands up, if you don't mind. Yeah. Though I don't know there's canonical ordering.
Goodness. So let's go with Sam. I think that I think I saw his name. Yeah, Samuel.
Oh, hi, thanks. Yeah, I actually have more of a technical question. I was just, I think you mentioned at some point, and I might just have missed it, that when you talk about these families of CFTs that you're able to, construct these measures and integrate over, I think you mentioned that you sort of go between these CFTs by some exactly marginal operator.
Indeed.
Do you have a construction of that operator in these cases?
I do. I wrote it down for you here. Okay.
Okay. Yeah. Okay.
And at higher central charge, it's products of dx's and d bar x's where you take different x's. Nothing fancy. I mean, this is an extraordinarily simple theory of CFTs.
Okay, great. I have another question, but maybe somebody else should go.
Well, why don't you ask? Why don't you exhaust your questions?
Yeah. Okay. Yeah. I guess. And then, my other question was just when you mentioned, I think that the second interpretation of this averaging, you talked about these self-averaging theories.
Yeah.
And I guess
you're not allowed to ask me questions about
that. Okay.
No, you can ask me a question.
I was just I was just wondering. I guess, and I'm not super familiar with this, but I've read about there's this difference between this quench disorder and this annealed disorder.
Yes,
is that
related
to this?
Yes, that I can. That I actually do know something about. So, roughly speaking, these sorts of things arise because what we're interested in, like, I computed an average of a partition function, but you should have yelled at me when I did that, because you should only ever average things that are extensive with volume, okay? Which means I should really talk about an averaged free energy. That is to say, the average of the log of the partition function. That's the only thing that ever really makes sense, is to, partition functions are not, like, you always want to consider things that are extensive. So you want to compute the average of the log of the partition function. The problem is that taking averages of logarithms is hard, okay, right? The replica trick is, at its core, a method for taking averages of logarithms, right? So one way of dealing this is to use the replica trick. Another way of dealing with this is to pretend you're taking the log of an average instead of the average of a log, okay? When people talk about the difference between quench disorder and annealed disorder, that's what they're doing. There is, so one could, that's the difference between quenched and annealed disorder, whether you take the logarithm first or not. I wish I knew how to compute the average of the log of z in this ensemble of CFTs. I think it is pieces of it I know how to compute, but not the whole thing. So I'm not gonna,
Okay, great, thanks.
There's more one can say. I had a paper with Netta Engelhardt and Sebastian Fischetti that we considered these sorts of things primarily in the context of JT gravity. But I mean, other people have also considered these things as well. If you want to, this is an interesting thing to do if you want to try and make the analogy between spin glasses and gravity as sharp as possible. Good. Maybe we should move on to other questions, though. I see there.
Great, thanks.
Should I just call on?
Elliot, I think, was next.
Okay, great.
Right, thanks. Yeah, I was wondering, so you said that to you the picture for wormholes was a bit mysterious, like in terms of geometric interpretation. To what extent do you think it's mysterious? Like, do we know anything about how to interpret that?
We know some things. I mean, I'm allowed to find things mysterious. This is my right. When I say it's mysterious, what do I mean? What I mean is that I do not have a, I mean, if you read the paper that we wrote on this, there are a lot more caveats and sort of parentheses in the discussion than I put in here. One of those parenthetical remarks is that when we have disconnected geometries, such as this case that I'm looking at up here, I don't have a clear interpretation for the terms, for each individual term that appears in the sum as a topology, as a topological tree manifold. Okay. Some of them are simple wormholes, of the form torus times an interval. something like that. But I don't have a generic interpretation for these. I think there's some ways you could sort of think about them, but I don't want to say too much because I'm still a little confused about that.
Right. Okay, thanks. I also have another question, if I'm allowed, which is, so you said that the measure, you had a conjecture for the measure over the space of formal field theories, and you said that you say more if somebody asks, so I guess I'm asking.
Yeah. So this Siegel-Wave formula comes from number theory. Okay. Here's the intuition. Here's the intuition. So let's think about the moduli space of tori on the upper half plane. Okay. So they're parameterized by a complex structure or a conformal structure that I label by a tau parameter. And then in every discussion of, like, let's imagine I wanted to integrate over this fundamental domain. The point is that I would integrate over points in this fundamental domain, but there's 2 points I have to be very careful about. There's this point here, and there's this point here. Okay. So what are those points? Those points are the fixed point of the modular transformation S and the fixed point of the modular transformation S times T. Okay. And what do these correspond to? These correspond to tori that have symmetries. Right. The S invariant torus is the square torus, which has a Z2 symmetry. And the ST invariant torus is a torus with Z3 symmetry that sort of looks like that. Okay. And so in the language of conformal field theories, if this is a target space, these would be CFTs with symmetry. Okay. And in particular, they would have either a Z2 or a Z3 discrete symmetry. And if you just read Apostle's book on analytic number theory, for example, and you'll see that in any counting formula, any integral formula, anything like that, this S invariant point counts with a factor of 1/2, and the ST invariant point counts with a factor of 1/3. Okay. So I'm taking that observation and I'm generalizing that. So I'm saying that if a CFT has lots of symmetries, it only counts as if it's a much smaller CFT. Okay. Yeah, that's the inspiration for that conjecture.
Right, thanks.
Sure.
I think Casey was next. Yeah.
Sure.
I should say that we're sort of, way over time.
We're deep into the landscape.
We're deep into it, which, I want the questions to go on. Maybe
I'm happy to stick around and answer questions, but we should give people permission to leave.
Right. And the other thing is that I wanted to announce is that next week there's a Q&A session on Monday that hopefully Alex will show up to.
Oh, when is it on Monday?
Let's see, it's oh goodness. I think it's the afternoon one.
Okay.
Yeah, so it's local time 2 to 3:15.
So okay, let me just. So that's 2 p.m. Colorado time.
Yeah.
Okay.
I can make it. So I mean, there will be 3 speakers. I mean, so hopefully showing up for that. And so if Alex can make that, then you'll have plenty of opportunity to ask more questions. But yeah.
Yeah, it's the same Zoom link, I assume.
Yes, everything will be this. Yeah, that's right.
Okay, great. I'm just adding it to my calendar.
Thanks. Yeah, so but let's just actually thank Alex for his beautiful series of lectures. And we can continue asking questions after this. I just want to go.
Yeah, thank you. And everyone has my permission